All right, in this video, we're going to transition to talking about the fourth major phase or section of the class, which is the section talking about what's called linear combination of vectors and what's called span of vectors. So, a linear combination of vectors is a combination that you get by adding together constant multiples of the vectors in your set. So a linear combination is one that has been created via constant multiples and via addition. So let me give you an example. I have two vectors here, v1 and v2, 1, 1, 0, and 1, 0, 0. So all of the following are linear combinations of these two vectors. If I take the vector v1 times 3, and then I add that to v2 times 2, this would be 3 times 1, 1, 0, 2 times 1, 0, 0. So that would be 3, 3, 0 plus 2, 0, 0, giving a result of 5, 3, 0. This vector 5, 3, 0 is a linear combination of v1 and v2. Another example, if I have just v1 minus v2, which you can think about as v1 plus negative 1 applied to v2. This would also count as a linear combination. I get 0, 1, 0. So this vector 0, 1, 0 would also be considered a linear combination of v1 and v2. Now it's also possible to combine the vectors just by taking one of the vectors and scaling it. So for example, 4v1 would count as a linear combination because you could think about it as 4v1 plus 0v2. So that would just be the vector 4, 4, 0. That would also be considered a linear combination of these two vectors. And sort of to take that even further, the zero vector, the zero vector itself being 0 times v1 plus 0 times v2, the zero vector is technically a linear combination of v1 and v2. So that's linear combination. Linear combination is a vector that can be produced by taking the vectors in your set and mixing them up, combining them using constant multiples and using addition. So the way I often think about linear combination is in terms of mixing colors together. You know, if you think about your vector v1 as being like red paint and your vector v2 as being like blue paint, then you can create different shades of red and blue and purple by mixing v1 and v2 together in different ratios. So you can think about a vector like 530 as being a specific shade of purple that has been created by mixing together red and blue in this combination. Now, you might recall that when we learned about vector scaling and vector addition, we had some ways to interpret those actions graphically. So for example, if my vector v looks like this, and my vector w looks like this, pointing straight upward, then the vector v plus w would complete that triangle, v plus w here. And if we have a vector v and we apply a scalar multiple to it, giving us, for example, 2v, then graphically we could interpret that as increasing or decreasing the length of the vector v, depending on whether we applied a large scalar multiple or a small scalar multiple. Now, if you combine these two properties, you can understand linear combinations through a graphical perspective. For example, if v is equal to this vector, and w is equal to this vector, and I wanted to graphically make sense of a linear combination like 3v plus 1/2 w, then I could understand this particular linear combination by taking the vector v and making it 3 times longer than it was before, so roughly speaking here is 3v in blue, taking the vector w and making it half as long as it was before. So 1/2 w would be here, drawing 1/2 w from the terminal point of 3v, somewhere over here, and then the sum 3v plus 1/2 w would be, by triangle rule, the vector that connects / completes this triangle. So if you bear the rules for vector scaling and vector addition in mind, you can interpret any linear combination graphically. And you'll see us doing that in the next several lessons. Having now defined linear combination, let me talk to you about this word span. You've already heard me use the word span here and there as we talked about vector projection. So let me now define this term span more rigorously and more clearly. If you have a collection of vectors, the span of that collection of vectors consists of all the possible linear combinations of the vectors in that set. So for example, if I'm thinking about the span of the two vectors given above, the vector v1 equals 1, 1, 0, and the vector v2 equals 1, 0, 0, let's go ahead and try and understand and describe the span of those vectors, all the vectors that you can get by combining these two in various ways. So let's imagine a sort of generic linear combination of C times V1 plus D times V2, where C and D are whatever real scalar values. If I follow through on this vector arithmetic, 1, 1, 0 and 1, 0, 0, and if I use PEMDAS, doing the multiplication first and then doing the addition, any possible linear combination of these two vectors must have a specific format. A real number in the first entry coming from the sum of whatever constant is on V1 and whatever constant is on V2. A real number in the y component coming from whatever constant is on V1 specifically. But then every vector in the span has a really interesting property. Every vector in the span of this v1 and this v2 has the property that the third entry, the z component, is 0. So the span of these two vectors consists of all the vectors in three-dimensional space that have a third entry that have a z component of 0. So what I could write is that the span of the set of these two vectors, this v1 and this v2, I would describe the span as all the 3D vectors that have 0 for the z component. In other words, all the three-dimensional vectors that lie flat in the xy plane. That would be the span of the two vectors in this problem, because that is the shape and the format and the nature of all the vectors that can be produced by combining these vectors in this way. So here in GeoGebra, these vectors currently in purple, this vector here along the positive x-axis, and this vector here pointing in the positive x and y direction, these are the vectors v1 and v2 in the problem. Now, what I have drawn here in black is the linear combination v1 plus v2. And to help me to see that, I've used a little bit of triangle rule here. I have taken a copy of the vector v2, and I've placed it over here so that it is emanating from the end of v1. So following v1, and then following a copy of v2 over to this terminal point. And then by triangle rule, if I follow v1 and then v2, the sum of those two vectors is going to be this black vector that brings me from the origin over to this corner point. So what you have here in black right now is the linear combination v1 plus v2. Now I have put some sliders into this GeoGebra module that'll allow me to construct other linear combinations of these two vectors. So for example, by adjusting this first slider, I can apply a different scalar multiple to the vector v2. So by adjusting this slider, I can apply a different scalar multiple to v2. For example, right here, this is the vector 2 times v2. And so this diagonal vector is v1 plus 2v2. That's this particular linear combination of these two vectors. I can also change the scalar multiple on v1 by using this other slider. So here, for example, I can slide this value out to 3, and now the linear combination that is in view is the vector 3 times v1 plus 2 times v2. 3v1 plus 2v2 is drawn as this black diagonal vector right here in the picture. And then by adjusting the sliders in various other ways, you can see the black vector adjust to show all the other possible linear combinations of these two vectors. And as you adjust those sliders to all of their possible values, both positive and negative, you can see this diagonal black vector reaching every single point in the xy plane and stretching out to every possible location in the xy plane. So this is the visual proof, and this is the visual explanation of why the span of these two vectors consists of the xy plane in three-dimensional space. Because if you combine these two vectors in every imaginable way, using all possible scalar multiples, both positive and negative, you can construct vectors that reach any possible location in the xy plane in three-dimensional space. Let's do this exercise one more time with another set of vectors. Here we have the vector v1 consisting of 0, 2, 0, and the vector v2 with entries 0, 0, minus 1. So let's describe what is spanned by these two vectors, both in terms of symbols and in terms of a picture or a graph. So if I answer this question symbolically, I'm going to imagine all the different things that can be constructed by putting these two vectors together in a linear combination. So I would have some number times a vector v1, whatever other number times the vector v2. This is the generic format of a linear combination of these two vectors. If I put them together using vector arithmetic, I get something that has at all times 0 in that x component, then 2 times c plus 0 in the y component, and then 0 minus d in the final component. So what I notice about all of the vectors that are created via the linear combination here is that all of the vectors, no matter what c is equal to, no matter what d is equal to, end up with a 0 in the x component. So the span of these two vectors would be all the vectors that have this property, that 0 is in the x component. In other words, the span of these two vectors would be all the vectors that lie in the yz plane in three-dimensional space. So here on GeoGebra in purple, I've drawn the two vectors v1 and v2 in this problem. So here's v1 pointing 2 units in the positive y direction, and here is v2 pointing 1 unit in the negative z direction. And what we have here in black is this vector v1 plus v2, that particular linear combination of these two vectors. Now, if I use these sliders on the right-hand side, I can construct other linear combinations of v1 and v2. For example, by scaling the vector v1 by some amount, either positive or negative, or scaling the vector v2 by some amount, either positive or negative. And if you allow uh, B and C to vary over all their possible values, then you can see that the combination of these two vectors is capable of sweeping out and generating every single vector that points in the YZ plane here in three-dimensional space. The YZ plane, which is currently drawn in blue, is the set of all the vectors that can be created by combining v1 and v2. Now, in both of the examples that we have studied so far, we were given two vectors, and the span of those two vectors was a two-dimensional object. A two-dimensional object meaning, for example, a plane. The span of these two vectors was the xy plane in particular. The span of these two vectors was the yz plane, and spans of other pairs of vectors can generate other planes that are tilted in other ways. However, under certain circumstances, you have two vectors, you calculate the span, and the result is not two-dimensional. It might be one-dimensional. And this is the situation that occurs if one of the vectors in your set is, in some sense, redundant or unnecessary. Let me give you an example of such a situation. So in this problem, the two vectors are v1 equals 1, 1, 0, and v2 equals 2, 2, 0. Once again, let's go ahead and describe the span of these vectors both symbolically and graphically. So first of all, in symbols, I'm going to go ahead and consider what would happen if I combine c times 1, 1, 0 with d times 2, 2, 0. If I combine those, I get c times 1 plus 2d, c times 1 plus 2d, and 0. So this result has two very interesting properties. The first property that I notice in this result is that the z component is always equal to 0. So that suggests that all these vectors must live inside the xy plane in three-dimensional space. But in this problem, that's not the only property of this combination that's interesting. The other property of this combination that's interesting is that the x component and the y component are exactly the same. The x here is equal to the y. They are both c plus 2d. So let's see how this additional sort of condition manifests graphically in the picture of the span of these two vectors. So this GeoGebra image was created using the same method and the same code as the other two GeoGebra modules that we've looked at before. But this picture looks a lot different than the ones that we examined before. And that's because in the previous GeoGebra modules, the vectors v1 and v2 that we were using to span the set, those two vectors pointed in completely different directions. What's different in this picture is that the vectors v1 and v2, which are spanning the relevant set, those vectors point in exactly the same direction. The vector v1 points 1 unit in the x direction and 1 unit in the y direction, so the vector v1 points this way. The vector v2, however, points in exactly the same direction. v2 is just twice as long as v1. So if we consider all the possible different ways and methods to combine these two vectors, we get a pretty limited set of results from those combinations. Because the two vectors already are pointing in exactly the same direction, because the two vectors are already pointing along this diagonal line, when we add them or subtract them or scale them, the result is also necessarily going to have to lie along this line in three-dimensional space. So in this particular case, because v1 and v2 were scalar multiples of each other, we ended up with a span that was not two-dimensional, not a plane like before, but a span that was only one-dimensional, in this case, just a line. The span of V1 and V2 is just the one-dimensional line that has the property that x is equal to y and z is equal to 0. This happened because V2 is actually itself a scalar multiple of V1. So V2 is redundant and already contained in the span of V1. So although there were two vectors, we ended up with a one-dimensional span because one of the two vectors was actually redundant and a duplicate in some sense of the first. So similarly, when we're dealing with a set of three vectors, in most cases, if you span three vectors, you're going to get something that is three-dimensional, like the three-dimensional world that we live in, right? So for example, if I have the vectors here, v1 equals 1, 0, 0, 0, 1, 0, and 0, 0, 1, the span of these vectors would be all of the vectors that have the following shape. Some number times 1, 0, 0, plus some other number times 0, 1, 0, plus some other number, k, times 0, 0, 1. If I combine those, I can get any number I want in the x position, any number I want in the y position, and any number I want in the z position. So the span of these three vectors is all of three-dimensional space. All of 3D space because any three-dimensional vector, any vector in R3, can be constructed by combining these three vectors in a certain kind of way. So the span of these three vectors is all of R3, a three-dimensional set. But once again, if you have a set of three vectors, and one of those vectors is somehow redundant, then you can end up with a span that actually is less in its dimension, a span that's two-dimensional or one-dimensional, depending on how much redundancy you have in your vectors. For example, here, if I had the vector v1 equals 1, 0, 0, and the vector v2 equals 0, 1, 0, but if my vector 3 is equal to 1, 1, 0, I think that this set contains a certain amount of redundancy that's going to limit what can be produced by the span of these vectors. If I first combine these vectors symbolically, whatever number times the first vector, whatever number times the second vector, whatever number times the third vector, pretty much no matter what I do, I'm still going to end up with a vector that has 0 in the z component. So by spanning these vectors, spanning three vectors has still given me a two-dimensional set in the end. It's still given me only the vectors that are in the xy plane, the vectors that have z equals 0. Once again, the span of this set of three vectors is only two-dimensional because one of the vectors in this set is redundant of the others. One of the vectors in this set is not really adding anything meaningful. And for example, here, I think the issue is that, we have this vector v3, and the issue with the vector v3 is that it already is a linear combination of the first two vectors. Vector v3 can be obtained by summing together v1 and v2. So vector v3 is already in the span of the other guys. So it's not really contributing anything new or meaningful to the span of this larger set. The way that I think about it, once again, is in terms of colors. If I think about the vector v1 as being like the primary color red, and I think about the vector v2 as being like the primary color blue, then in this instance, the vector v3 would be like the color purple. It's a color that you can obtain by mixing together blue and red. You're not really getting any extra colors in your color palette by including V3 because V3 can already be obtained by mixing together V1 and V2. So this brings us to a pretty important piece of terminology in this class, which is called linear independence. Linear independence, once again, is trying to capture this idea of redundancy between vectors that we've encountered in a couple of problems by now. In plain terms, a set of vectors is called linearly independent if none of the vectors in the set are redundant. We say that a set of vectors is linearly independent if none of the vectors is contained in the span of the other vectors. Vectors are linearly independent if none of the vectors can be formed by combining the others. We could also say that a set is linearly independent if you can put them together and span a full n-dimensional space. So in other words, this set of vectors was linearly dependent because although there were three vectors, it only spanned a two-dimensional space. But these vectors were linearly independent because there were three vectors and they spanned a three-dimensional space. So that's what that last phrasing, that last condition is trying to capture. If you have n vectors and those vectors span something that is n-dimensional, then that means that none of your vectors is redundant. All of your vectors are meaningful and distinct from each other, and so those vectors would be called linearly independent. Once again, you can make sense of this in terms of real world stuff. A linearly independent set in like food. Simple food example would be peanut butter, bread, and jam. All of these are completely different, distinct ingredients. But a linearly dependent set of foods would be peanut butter, bread, and a peanut butter sandwich. This is linearly dependent because you can make a peanut butter sandwich by combining peanut butter and bread. For an example of linear independence, if you're dealing with paints, if you have red paint, blue paint, and yellow paint, you can mix whatever color paint you want. But a linearly dependent set would be red paint, blue paint, and purple paint, because you can create purple by mixing together red and blue. So independence means no redundancy. Dependence means there is some redundancy. So let's return to our previous examples and talk about them in the new language. The vectors that we saw, v1 equals 1, 0, 0, v2 equals 0, 1, 0, and v3 equals 0, 0, 1. These vectors are linearly independent because when we examined the span, these three vectors spanned all of three-dimensional space. By contrast, this set, 1, 0, 0, 0, 1, 0, and 1, 1, 0, these vectors were linearly dependent. And the two ways that we detected that, one is that these three vectors only spanned a two-dimensional set. When we looked at the span, it was just a plane. Another way to tell that these vectors are linearly dependent is that we see that we can create V3 by combining V1 and V2. So V3 is redundant and unnecessary in this set. The vectors that we saw at the very start of this lesson, V1 equals 1, 1, 0, V2 equals 1, 0, 0. These vectors were linearly independent. When we looked at the span of these two vectors spanned a two-dimensional space, the xy plane. But when we looked by contrast at the set where V1 is 1, 1, 0 and V2 was 2, 2, 0, these vectors were linearly dependent. Two ways to see that. First is that although we have two vectors, the span of these two vectors was one-dimensional, just a line in space. The other way to see that is to notice that V2 can be constructed just by applying a scalar multiple to V1. So V2 is redundant. You don't need it if you have V1 already. Linearly dependent. So that concludes today's video. Today we introduced the language and the concept of a linear combination of vectors. A linear combination of vectors is a combination that you get by scaling the vectors and adding them together. Using the triangle rule, for example, and using our graphical understanding of vector scaling, you can interpret any linear combination in a graphical way. The span of a set of vectors is the collection of all possible results of all possible linear combinations of those vectors. Sometimes when you span two vectors, you get something that's two-dimensional. Sometimes when you span three vectors, you get something that's three-dimensional. But sometimes there is a redundancy in the set of vectors that you're using to do the span. And if there's a redundancy between your vectors, the span usually ends up being smaller than it seems like it should be. So if you're in a situation where one of your vectors is redundant, if you're in a situation where one of your vectors can be constructed by spanning/combining the other two, we say that vectors in that situation are linearly dependent. Whereas if there's no redundancy between the vectors in your set, those vectors are said to be linearly independent.